I don't remember talking about it. Did we talk about DF betas or DF beta at all?
What's that?
DF betas or DF beta?
The DF beta. The DF beta actually literally is associated with the individual parameter. So if I have a model, such as y equals b0 plus b1 plus b2, it'll actually give me a standardized or unstandardized value to see how much that parameter estimate changes. So that was not required.
Okay. I tried to run it, but it made my data all funny, so I wasn't. It kind of.
Yeah.
I don't know if that was just my computer being silly or.
Let me take a look here, because usually it's just another diagnostic stack. So
yeah.
If I do save, let's just do DF beta, standardized DF beta right there.
Well, what I did is I tried to exclude like some of the top DF betas. I don't know if that was accurate to you, but
yeah. So it's right there. So there it is for there it is for one predictor for health. There's a standardized for social support,
yeah.
Standardized for well-being, and then the intercept.
But when I tried to screen, like kind of take out some of the DF beta outliers at the highest values, to make my data weird. Okay. Would you do that?
Not for DF beta. No, I don't use it much, and it probably is a helpful diagnostic to really focus in on the specific parameters. I don't use it much. With my global indices, the leverage, the Cook's distance, standardized residuals all look fine. I don't worry too much about that. But you could try something like that. You could. I mean, I tend not to, but I usually just don't use them very much. Remember, guys, if you keep running the same model over and over again, look at all these things that are added, right? So keep that in mind. If you run the same model, but you don't need the diagnostics anymore, just you might want to keep that in mind. Okay, any questions then on the homeworks? Okay, cool. Let's continue where we were, everybody. Now let's get into our in-class example. Hopefully you've been printing out the handouts. I don't know if you have been. That'll help guide you with each of the chapters. So there are handouts. There's the notes, and then there's a separate folder of the handouts. So let's go to an example of a two-group MANOVA, which we left off on page 146. We talked 2 weeks ago. We talked about all the reasons why you would use a MANOVA over a NOVA. And now, again, I'm just going to go through the math so you see it's not just a black box, but you will not have to do it by hand. You would have been one of the few people in San Diego that would have done a MANOVA by hand. That used to be a homework assignment. You did for a small sample size. But now at least I want to at least show you how this works. So I have this database of job satisfaction and job involvement. And let me even see here if I have the data right there. Open data. Here's just a small little data set. Small little data set. And we have very small sample size for Amanda. Right? Very small sample size. But we have 5 people in the autonomous work group, 5 people in the power. So that's one of the early IO projects I was on, actually, before I became more of a stats guy. But I actually helped with Sharp Grossman Hospital. These various groups become autonomous work groups. Has anybody heard of those before? People make up their own decisions. Where it got tricky is once things went into compensation, they realized how powerless they were. So they could do maybe things within how they would do tasks, how they would maybe delegate. Once it got into kind of almost HR type stuff, things got very tricky with autonomous work groups. And very tricky and political. And then empowerment, right? So here I've got 2 DVs. Very simple model. Job satisfaction and job involvement. So here I've got the data set up right here. Does everybody see we have 2 groups and each one has 2 outputs, right? So here, first, here's the mean for each of those. And this just follows along the calculations, everybody, from the book on page 147 through 149. So, do you see we have a mean of 5 and 4 and 5 and 3 for each of the groups? So now, everybody, do you recall in ANOVA you broke down sum of squares due to what? In ANOVA, you broke down sum of squares to Between and within. Thank you.
Oh.
Wow.
Thank you. Thank you. Thank you. You guys, it wasn't.
I did break
I don't do trick questions, you guys. It was just a very simple question. Okay, you look like deer in the headlights. So,
Well, it's pretty early.
what's that? So some squares between within. But you're going to find we do some parallels in MANOVA. It's just kind of more. So here, now what you got to create, the first one is a within matrix for each group. I'm going to create a within matrix. How many DBs do I have? 2. So I have the sum of squares of the first outcome, sum of squares of the second, which is always on the horizontal. And what's on the diagonal? The diagonal. What's on the off diagonal? Remember in correlations you have variance, covariance. It's the covariance. So here, everybody, to compute the sum of squares, and I'm not going to go through the entire math, but just so you kind of see where it comes from. I'm going to take each score from the mean square, each score from the mean square. Doesn't that kind of look like a NOVA? Right? Remember? That captured the within group, and that's the 10. And then I could probably do it for the other one. 2 minus 4. 5 minus 4 is 8. So do you see it's like kind of starting off with doing a NOVA, right? And I probably then have to do it for the next group, right? 5 minus 5 squared, 6 minus 3 squared, etc. Right? So I'm going to get a sum of squares for each group, for each DB. And then the covariance, 3 minus 5 times 2 minus 4, plus 4 minus 5 times 5 minus 4, right? Because if you recall, the covariance, everybody, of x and y is x minus the mean of x times y minus the mean of y, right? N minus 1. Right? So the covariance is just taking each score from the mean from each of the variables. So you get a covariance for each of these, which means our first within matrix is a 10 and an 8 and a 4 and a 4. Because the off diagonals will always be the same, because it's a covariance, right? The covariance of 1 and 2 is the same as 2 and 1. So now you have basically the sum of squares and cross products matrix. Right? And think about it, the sum of squares and cross products. And I can do it for the second group. So now I have an autonomous work group and a parametric work group. I basically have the within variability matrices. Does everybody see how we got that then? And this follows straight from the book, everybody. Straight from the book that shows how to get up in within. Any questions on this so far? Again, you will be saved from having to do this as a homework. In the old days, you had to do all this by hand. I still think it would be fun for you to do, but you don't have to. Which means you get now basically a variance-covariance matrix, combining, pooling together information from both groups. Pooling together. Which means S will be 10, 4, 4, 8, right, plus. And remember, when's the only time you can add matrices? When they're what? When can you add matrices? Same dimensions, right? 2 by 2, 3 by 3, 4 by 3, etc. So of course these will be the same. -1, -1, 6. So now do you see we're going to add basically these sum of squares cross products for each of the groups. For each of the groups. Then you're going to divide it by 5 plus 5 minus 2. What do you think the 5 means, everybody? Where do you think I got that from? Sample size of each group. Right? There's 5 people in each group. 5 plus 5 minus 2, so it's kind of like the degrees of freedom, so to speak. And when all is said and done, what's that?
Where's the minus 2 come from?
The minus 2 because you suck away a degree of freedom for each group. There's 2 groups. Okay. Kind of like a t-test, right? Remember, n minus 2? In fact, it is a, that's why the book starts off, this is a multivariate generalization of a t-test. See, it really is like a t-test in the NOVA stack. It's just kind of more. Just more. You know, it really is. It's a t-test in the NOVA, which is more. Except when we get to logarithms. Then that's different. That's truly different. So then, everybody, I've got 2, 0.375, 0.375, 1.75. In other words, I took each of these. 10 plus 6 is what, everybody? 16 divided by 8 is 2. Right. All right, so I'm taking each of these and dividing them. I'm taking each of these. So there, everybody, is your basically a variance-covariance matrix. A multivariate. A multivariate. So now you've got S, everybody. Now you've got S. Any questions on this so far? And again, this follows along, just so you want to kind of get an idea of where I'm getting all this from. It's on page 150 to 151. It just follows how to get at the multivariate test. So now, you have to calculate the determinant of S. This is when we start deviating from a t-test. So now, remember the determinant, everybody, which is a generalized variance. And do you recall what you have to do to get at a determinant, everybody? Do you recall how I can get a determinant for a simple 2 by 2? Nice. Remember, I never went beyond a 2 by 2, because then you have to do what's called co-minor, right factors. Do you recall it's just 2 times 1.75 plus what, everybody? 0.375 squared. You got it. Right, remember, you just go ahead and multiply. Multiply each of those. You got it. And then this equals 3.36. Now you've got the generalized variance for the within group matrix. You've got one number that literally encapsulates the entire relation between not only two groups, but two DVs. So now you've got to do the fun stuff. What's the fun stuff? What does that mean? Invert it. Right? Got to invert the matrix. Got to invert the matrix. Which means you just take each of these components, right? And I'm going to go ahead and do 1.75 divided by 3.36, 0.375 divided by 3.36, 0.375 divided by 3.36, and 2 divided by 3.36. And I know this may seem kind of weird, but do you recall when you have the determinant inverted, you switched. Right? If you recall, you switched them, doing what's called cofactors. So when all is said and done, everybody, when all is said and done, this equals 0.521, negative 0.112, negative 0.112, 0.595. Where do the negative signs come from? You've got to add those. Right? Once you do that, once you take the cofactors. So now, everybody, you've got the inversion of the variance-covariance matrix, essentially, from a multivariate design. So now we're kind of deviating from the t-test a little bit, aren't we? Yeah, a lot more. So now you've got kind of the denominator for your ANOVA, your MANOVA, right? Because it's capturing, it's all started from here, everybody. It all started from your variance-covariance matrix. Oh,
no, it's true.
Oh, it's just a sure. You would tell me if it was. Thank you. There we go. So now, so this is the fun stuff you used to do for homework. Chad, are you kind of excited about doing it? Very disappointed. Okay. Can you sign it, Chad? I still have it in my phone. Yeah. Well, I don't want you to be.
I'm sure I can find something else to occupy.
Just be a couple hours. So now, everybody, can I erase this? Are you guys okay with this so far? Excellent. So now you've got the within group, and now you get what's called the multivariate T. The multivariate T, as opposed to the univariate, which means it's going to be a function of 5 times 5 divided by 5 plus 5. It's just, it's just basically the sample sizes. And then 5 minus 5, 4 minus 3. Anyone like to guess where I came up with that? 5 minus 5, 4 minus 3. Very, what? The means, you got it. Kind of like a t-test, isn't it? for one DV. So this is what's called a mean vector. It's a mean vector, right? Mean of one group minus the mean of the other. Mean of the other group minus the mean of the other. It's called a mean vector. It's totally focusing on the means, which probably serves as what, everybody? The numerator denominator for the t-test or ANOVA. The difference in the mean. Think of good old t-test, everybody. Serves as numerator or denominator. Yes, numerator. Just like a t-test, right? That's why the book has a nice little table, page 150, God bless you, kind of showing the parallels of the t-test univariate and the t-test multivariate. So now you've got this, which takes into account not only sample size, but also the means for each of the groups. And then, everybody, then you got to multiply this by 5 minus 5, 4 minus 3. And let me do this longhand here so you can see exactly what's going on. T squared equals 5 plus 5 sample sizes, a mean vector, which is a row or column vector. Is that a row or column vector? Thank you, row, you got it. And then 0.521, negative 0.112, negative 0.112, 0.595, which you can recall is going to be the denominator, right? Because it's a determinant. And then 5 minus 5, 4 minus 3, which is what? A row or column vector of the difference means. This is a row vector. This is a column vector. Exactly. Row vector, column vector. So now what you see, everybody, is you're taking into account the means and the within group matrix, which is kind of like a t-test or an ANOVA. And when all is said and done, everybody, once you do all the math, 1.4875. 1.4875 is the result. It's basically your t squared. Is your t squared. And you can convert it to an f. Because if you recall, t squared equals f. And there's a way to convert it. So one thing I want you to see by the formula is we took into account the means for each of the groups for the multiple DVs, and then we took into account the variance-covariance matrix for the within-group variability, but in a very concise way using matrix algebra. Now, can you imagine if you had 300 people and 4 groups and 6 DVs? Would you want to do that one by hand? You can do it. That's when you let computers do their work. The F, which is in your book, everybody, the F transformation is 5 plus 5 minus 2 minus 1 over 5 plus 5 minus 2 times 2. And then, which equals 7/16 times our t squared. 1.4875, which equals 0.65. That's just, again, looking at the formula that you have on page 151, which is an F transformation of the t squared. That, my friends, there's a few other little funky mixture. That is the math. That is kind of the math for a ANOVA. How easy schmoozy, huh? So let's run it. Let's run. And you do have this on your handout. Analyze general linear model multivariate. So you go to multivariate everything. Put in the group under fixed factor, and as you would guess, each of the DVs under there. So there's the multivariate, everybody. For now, under options, it's always good to get descriptive stats, effect size, and I'm going to get an homogeneity test. We're going to talk about all of these. I'm going to get a few other things here, though. Parameter estimates, sum of squares, and residual, because this is going to show you some of the stuff we did by hand. So now you see we have a MANOVA, everybody. The book the text is just GLM. In the old days, you had to use syntax called MANOVA. But you have 2 DBs by group. Add. Do these means look familiar, everybody? 5 and 5, 4 and 3. Do the means look familiar? And this is in your notes as well as your handout, everybody. We're going to get to boxes and tests very soon. And Barclay's test. And here you have the multivariate test. Does that 0.65 look familiar? There's the 0.65. There it is, everybody. There's your F. There's your F right there. So you see there's a lot of stuff that goes on behind the scenes before you get the F. I had to do all of this computation to be able to get at the t squared, taking into account the within group variance, which was a function initially of sum of squares of each group, right? It was basically a sum of squares cross product matrix for each group, and it distilled it to one matrix. Then you just had the mean vectors, one as a row and one that was transposed, right? So basically, if this is yi minus y2, this would be y1 minus y2. And what does that little thing right there mean, everybody? Or apostrophe? Transpose. Transpose. The row becomes a column, or a column becomes, you got it. You got it. And there's your test, everybody, with 2 and 7 degrees of freedom. 2 and 7 degrees of freedom. So you have what's called the hypothesis degrees of freedom and the error. So these are the degrees of freedom, everybody. Don't worry about the intercept for now. So here you have the F is 0.65. The p-value is 0.55. Reject or fail to reject? Fail to reject. You got it. Fail to reject. But what I'm going to show you, everybody, I'm going to show you a couple of things here. Early on, we did some computations. You may not remember, but we had one matrix that was 16, 3, 3, 14. Some of those look familiar. There's the between subject sum of squares cross matrix. And look at this, everybody. 2, 1.75, 0.375. Right there under what's called the residual sum of squares, there's the matrix we did by hand. Remember the 0.375s on the diagonal, which capture the sum of squares for each group? So you see it right there. That's a way of actually confirming your math. That's a way that you actually confirm your math, getting the residual sum of squares cross product. So looking at page 150, everybody, you can see the parallel between a univariate and multivariate T. Right? The sum of squares for univariate was a within group matrix for each of those groups. You added them up, you pulled them together, then you divide by the degrees of freedom, n plus n minus 2, which gave you the variance-covariance matrix. So it really is an extension, as you just saw, of the t-test. But it's just a lot more. It's just quite a bit more. What we ended up getting is what's called the Hotelling's t-square. It's the multivariate t. This is the Hotelling's t-square, which is the multivariate generalization of the t-test. Just a lot more. So now you kind of have an idea of the black box behind a MANOVA. And you saw when we have those groups, you put the 2 dBs there, with a fixed factor there. And it's always a good idea. Start to get the descriptive stats, effect size, the homogeneity test. And there's the syntax, everybody. The syntax is right there where you see you have 2 dBs by one group. 2 dBs by one group. And we're going to get to this fairly soon. Now, I just want to interrupt this, which you do have in your notes. I want to interrupt this with a MANOVA command, which we used to have to use in the old days. We used to have to use in the old days. This is MANOVA, job sat, job involvement with group. Looks kind of similar. And and I'm going to show you, everybody, what it does spit out for you. The stuff we did by hand. What's kind of nice about the MANOVA is that 10, 4, 8 with there. That was the first, right? That was the first variance-covariance matrix we got for the sum of squares of group 1. Job sat, job involvement for group number 1, 10, 4, and 8. And for group number 2, there's the 6, negative 1, 6. So it's kind of what's cool about the MANOVA. It'll show you exactly the sum of squares for each group. And in the old days, you have to do this by hand. You obviously don't have to now. But you had to calculate a determinant of the covariance matrix of DBs. Then you had to take a logarithm. The logarithm helps you get to the final solution. If you took a log of 2.19, I guarantee you would get 0.78. Which means that MANOVA shows us exactly what we did by hand initially. And all these multivariate tests are basically functions of eigenvalues. Eigenvalue is a critical element in breaking down variability. So first of all, you should see for now a lot of this mirrors what you've done in ANOVA and t-test. And we're going to come back to this, but here what can be a little confusing the first time you run a MANOVA is you get lots of tests of significance. You get lots of tests of significance, which can be a little confusing. Because, look what you get here, everybody. You get a Palais trace, you get a Wilks lambda, you get a Hotelian's trace, you get a Roy's largest root. And that can be a little confusing, but you get 4 tests of significance. 4 tests of significance. And which one do you pick? You're soon going to see that when you have 2 groups and 2 DVs, the minimum design, they're all going to be the same. They're all going to be the same, pretty much. So what are they functions of, everybody? What are they functions of? Wilks lambda is the one we'll pretty much focus on for this class. It's got some of the better properties, and you're going to see it's a little bit easier to interpret. The Wilks lambda is kind of like the percentage of variance accounted due to error. In other words, it is a function of the eigenvalue of error over the hypotheses plus error, which is kind of like error over between plus error. So that's kind of like total, isn't it? And it's a determinant. It's a determinant. So Wilks lambda is kind of like bad stuff over total stuff. So here you're going to see SE represents the error of sum of squares cross matrix, and SH represents hypothesis. So it's a function of error over total. And it's the one that a lot of people tend to report. Hotelian's trace is kind of similar, but what it does is sums up. It takes the inverse of the error matrix over hypothesis. So it's good stuff over bad, and basically sums up all these eigenvalues. And eigenvalue is a way of breaking down variance. And then there's Roy's largest root, which is a function of the eigenvalue, lambda over 1 plus eigenvalue. And then Palais trace criterion, which also is a function of eigenvalues. So all these get a little bit complex, everybody, because you have to break down to understand eigenvalues. There are many journal articles that show which ones perform best under which conditions. Some are more sensitive to smaller sample sizes versus larger sample sizes. For our purposes, I'm going to be fine with you just focusing on Wilks lambda. Yes, Jess?
Back to eigenvalues real quick. Is there, I went looking yesterday because they kept popping up and I know I learned about them in past classes, but I'm still not clear about, I know that they're important, obviously, but how do we talk about them when we're reporting?
Well, it depends. For this, for the MANOVA, you won't have to report it, really. I mean, it's going to be kind of the black box that gets at variation, and for the test statistic, where you will be talking about them is when we get to factor analysis.
Okay.
Once we get to factor analysis, soon you're going to see eigenvalues are used to break down, again, variability for each construct or factor.
Yeah, I went all over the internet and it was
Yeah.
It was complex. It wasn't just.
Yeah, no,
this is what I'm doing.
matrix algebra, there's entire chapters just on eigenvalues. Because they're actually a product of what's called a quadratic function. They're not easy to compute.
Yeah.
But for our purposes, we'll really get into them when we break down variables.
Okay.
So which is best? Roy's largest root was most sensitive when centroids differed along a single dimension, right? A centroid is like a mean in space, and the cases that deviate from it. Roy's criterion was most robust to violations concerning homogeneity of covariance matrix. We're going to get into that. Under diffuse, non-centrality, the ordering was Palais, Wilks, Hotelli, and Roy's. When sample sizes are large, they're all pretty much equivalent. So you get different results sometimes, especially, you know when it gets screwy, you guys, in applied research, when I use this stuff on sample sizes of 20. For my own research, I have found when I have small sample sizes, and I'm going to do a MANOVA, which I usually don't recommend to do because I think we need larger sample sizes, that's when you'll see. Otherwise, they rarely will contradict each other. So for our purposes, you guys, I'm absolutely fine with using Wilks Lambda for this semester. And what's kind of interesting, do you see here, remember our F was 0.65, do you see the Wilks Lambda of 0.143? What's 1 minus 0.143? Oh, I see this calculator. Let's do this by your head. What's 1 minus 0.143? What's that? Partial A squared. Because remember, it's a function of, remember that basically Wilks lambda is essentially the determinant. Wilks lambda is essentially error, the determinant over total. That's Wilks lambda, everybody, error over total, which means bad stuff over total stuff. So 1 minus lambda would be what, everybody? Partial A squared, your effect size. Does everybody see why that would be the case? If you have bad stuff over total stuff, if I subtract that from 1, guess what? There's your partial A squared, your multivariate effect size. So that is a multivariate effect size. How do you explain 15%? That means 15.7% of the variability. Okay, we'll talk about this. 15.7% of the variability in the linear combination of the two outcomes. Do you see what I'm saying, you guys? It's a linear combination of the two outcomes as explained by the grouping vector. Autonomous work group versus empowerment. So now, it's not just one DV, is it? How many DVs do we have? How many DVs do we have? 2. So it's a linear combination of 2 DVs. And there it is, everybody. F 27.65. P equals 0.55. Or you may do this. Well, it's lambda 0.843. P equals 0.55. Eta squared is 0.157. Depending if you want to report the F or Wilks lambda. And that's it, everybody. That's it for your first MANOVA. Any questions on this thus far? Any questions on the MANOVA?
We do not have solutions.
We do not. We failed to reject.
Which means that this isn't a good model for...
I guess you could say, what do you mean this is not a good model?
Well, I'm trying to figure out how I would explain that to someone.
If this was your real data, there's one easy explanation. I mean, besides the means being kind of close, what would be your other concern? Jocelyn, looking at this. Let me help you.
Oh, collinearity.
I'll help you again.
So that's the bad stuff. They're all equal?
Small sample size.
Oh.
I try to get that to you. 5 people in each group, right? Small sample size, right? So is it harder or easier to reject the null when you have a large sample size, small sample size?
It's harder.
Yeah. So I'm not saying getting a larger sample size will guarantee significance because you still may have.
Well, would you do this with just that many people?
No, but I did last week for Clyde, 13 people. It's really want to do a MANOVA, and I gave my caution. So just like, I rarely would do it. She has 13 people, and it's a MANOVA. She's got 3 DVs, 2 groups. I said, just don't trust the results. Do not trust. So yes, I've done it, but generally some of these multivariate statistics, they like larger samples.
Does that client just have enough information to be dangerous?
You know what I said, she can kind of treat it as a pilot. Barely, even barely as a pilot. 13 people. I said, I would not treat it as anything empirically you're going to make any broad proclamations. So you got an idea of the effect sizes, you got kind of an idea of effect sizes, you got an idea if the study even was feasible, but I would not, really worry about p-values.
Yeah.
No.
Okay, thank you.
So there's your multivariate test, everybody. Any questions so far on the MANOVA? Okay, everybody, then, remember good old Levine? Remember good old Levine from ANOVA? Again, keeping in mind small sample size. Happy or sad when it's not significant? Happy. Because then it means the error variances. Remember everybody, it's the error variances of the DV. And then, if we have significance, everybody, if we have significance, then you can drill down to the univariate display. You get the univariate result. So now you can see if there's group differences on either DV, job stat, job involvement. So now you see we got the multivariate test, which takes into account the linear combination of the multiple outcomes. And then if you have significance there, if you reject the null, you can drill down further. And we don't have significance for job stat and job involvement. Why is it no surprise that P is 1.0 for job stat? Why is it no surprise that P is 1.0? They have the same means. 5 minus 5 is what, everybody?
Oh yeah, that's what I was talking about before.
Yeah.
The means.
Yeah, these have the same means. So guess what the numerator is going to be? 0. So here, everybody, we can see more of the variance, and the only variance has to deal with job involvement. So here you can drill down to see if you have significance. And here's your one-way ANOVA, everybody. I just want to show you the univariate result is the same as a one-way ANOVA. Because look, if I run one-way ANOVA, do you see the P of 0.266? 0.266, F1.43, this is my one-way ANOVA. It's the same. It's the same as if you ran the one-way ANOVA. So this shows you the gains in power you potentially have by doing the MANOVA. If you have multiple outcomes and they're logically clustered, then it makes sense to run them as a MANOVA and then drill down. Any questions on this so far then, on the MANOVA? Any questions? Now, the book goes into a bit on post hoc test. Does a post hoc make sense for 2 groups? No, right? Have you ever tried to do a post hoc on 2 groups?
Probably.
What type?
I won't lie.
What type of message did you get?
Does not compute.
Okay, so you did a good old Tukey, okay? Did you get a little error message like this?
Yeah.
Is post hoc or not performed? Because 2 groups, right? Right. Yeah. So there's a little error
So I
message.
go in and I play around a lot, just
To see what happens.
yeah.
Mhm.
And that's how I learn doing. And then
Oh, I've made hundreds of mistakes with error messages. Things that I've had to learn, especially when I've had to learn something a little different than doing only syntax. That's how you learn. You get the errors and you try to rectify it. You try to rectify it. So that being said, everybody, soon we're going to get into these assumptions. Bartlett's test and Box's test. We'll get into that, especially in the next chapter. Now you guys now know the MANOVA. You now know you can get post hoc tests. All the post hocs that are available to you in one-way ANOVA are available to you in MANOVA. All of them. I do want to say, I talked briefly last year about games hell, right? Do you guys remember me talking about that? Again, that's a nice post hoc if the variances are not equal. And that's the one I tend to use. If homogeneity variance assumption is not tenable, I do tend to use the games hell right there. That's got some nice properties. Otherwise, I'm fine with the Tukey B, is fine if you have unequal sample size. If you want to be more conservative, we can use the what? The Chaffee. And the done it is used when you have what? The done it is used when you have a control group. Right, a control group. You got it. You got it. Any questions so far? Any questions so far? Okay. Multivariate test, but no univariate significance. Do you think that's possible? Do you think it's possible to have p less than 0.05 for a MANOVA, and then you drill down to the ANOVAs and no significance? Do you think that's at all possible?
Yeah.
Can you
Maybe,
yeah,
well,
can you-
because you're putting them all together.
Okay, okay, go ahead.
So all together, they're good predictors?
Okay, elaborate on that.
I don't know how to make work. If you're combining them, if you're combining all the predictors,
Uh-huh.
together they might be good, but separately they're not.
Yeah, you know what? You kind of got the hang of it. Because this is a multivariate problem that the joint combination of the variables might create, right? The joint combination, the joint probability of all these outcomes might create significance. And once you drill down to the individuals, it's not. Is it possible to have a nice R square in a regression, but no significant predictors? Is it possible to have a significant two-way interaction with no significant main effects? Absolutely. Because now we're talking about a multivariate problem, right? When you think about these, you know, once you start plotting things in space, when you think about this almost geometrically, and then let's say we have a centroid, right? Maybe you have, these are means for autonomous work group, and this is for the empowerment. And then you've got all these cases that deviate, right? So a centroid is a mean in space, and actually with Mahon-Point distance, which you remember, Mahon-Point distance is actually a function of the difference in these means divided by good old VarianceCovariance Matrix, which you just saw how to compute with the MANOVA. Here, the combination of these may create differences, but then once I analyze the group there, once I analyze, right, the groups there, once I analyze them right there, on their own they're not significant. Which means multivariate could potentially have, right, a nice gain in power. Right? As the book indicates, it's not always the case. Rejection of the multivariate test is not guaranteed that there will be one significant univariate F for a given set of data. Right? So it's always the combination of the variables. So keep that in mind. Just like you can have significant R square of, say, 13.5% for multiple regression, with no significant regression coefficients. Right? With no significant partial. I want to use the word partial. Because then, again, we're potentially going to have collinearity. The book then uses segues to a brief description and comparison to multivariate regression. And you're going to see some parallels with multivariate. And you learned multivariate regression at the end of the last chapter. Do you recall multivariate regression looked at what question, everybody? How did multivariate regression differ from multiple regression? That was the end of the prior chapter. Multiple outcomes, and you got it. So it's like you have two sets of variables, right? So here what I want to show you is, what if I ran multivariate regression? Keep in mind our MANOVA, right? 0.651, 15% accounted for, P of 0.55. Here for MANOVA, I ran this in the MANOVA syntax. And look, I get the same results. I did a multivariate regression, everybody. Look at that, everybody. P of 0.55. There's your F of 0.65. and I get my R squares. We already knew it was 0 for job sat because there's no between group differences. And we knew it was 15% for job involvement. So I get the same results when I do a multivariate regression. And here I can show you, if I do this by point and click, everybody, analyze, multivariate, and just put group as a covariate. Just shift it over as a covariate, everybody. Or not. Right? Gives me a multivariate test, P of 0.5. There's my R squared 15%. There's my R squares for each of these. It just serves as a covariate. But now I get something a little bit different. I get regression coefficients because this is a regression problem. So I do get a slope and an intercept for each of the groups. And what's interesting here, everybody, I get the residual sum of squares cross matrix. It's exactly the same. So it's a type of multivariate regression, everybody. Which means, again, as you've heard me say many times, ANOVA is just a type of way. ANOVA is a type of, which all falls under the rubric of what? The general linear model. You got it. You got it. Any questions so far? Any questions so far? And again, to repeat, it is possible to have significant multivariate but no univariate. It shows the beauty of a multivariate strategy. And again, the beauty of ANOVA is looking at that matrix. Sum of squares 1, sum of squares 2, and we're taking into account the covariance. So you're gaining your power. Okay, multivariate and power. Again, power is a function of what, everybody? Power is a function of sample size. You got it. What else? Larger or smaller effect size? Larger. This is irrelevant for ANOVA, but directional. One tail versus two tail. Right? It's kind of relevant because you can't set tails. You can kind of play around with things, but for our purposes, directionality is not relevant to multivariate. Because it's kind of multi-directional. At alpha level. Set an alpha higher, right? Remember, everybody? Set alpha higher, easier to reject the null. So we do gain some power by ANOVA. I want to show you using G-power. This confirms the table. There's a nice little table, everybody, on page 167. I mean, no, I'm sorry, not that table, but I'm going to confirm the results there, and then on page 168. I'm going to show you a couple things about how to do power for ANOVA. So, ways to improve power, page 164, right? Adopt a more lenient alpha, but have fun getting published. If you use an alpha of 0.10, the probability of getting published will be sorely diminished. Number 2, use one-tailed tests. But again, that's not an option in ANOVA. There's no point click for one-tailed. Consider ways of reducing within group variability to have a more sensitive design, right? In other words, try to reduce this thing right here. Your VarianceCovariance Matrix within. Or try to do whatever. If you can't impact variability on the within, what's the other thing you would try to impact? The mean. Your intervention, come up with a better intervention, right? A better mousetrap, right? So that being said, the book actually offers a couple different effect sizes, but now this is a little bit different, everybody, from ANOVA. So here, I want to confirm part of table on page 168 for 2 groups, 3 DVs, and a d square of 1.0, which is a standardized effect size. Remember Cohen's delta, which was a mean minus a mean over what? Good old Cohen's delta, the simplest t-test for its simplest power method for 2 groups. Group 1 minus group 2 over sample size free power. No, effect size is free of you guys will remember. I can see Chad's ready just to spit it out, right, Chad?
I might have it if I was a morning person. Hey, I think that's valid. Back it up.
X1 minus x2 over standard deviation. Right. Now, this gets tricky for Cohen's delta. Which standard deviation do you use? You have two groups.
Wait, what's the difference between Cohen's delta and Cohen's alpha?
Never heard of Cohen's alpha.
Oh.
Are you thinking of Cohen's alpha?
See? It's early for me. I'm telling you.
It's 10, 11. Half the day's gone.
Half the day. Time do you wake up?
Porsche.
Oh, are
Do
you
you really?
serious?
You can get out of the water pretty early these days. It's light at 10:06. So, the tricky thing is, do you use the standard deviation? Do you pool both of them together? Do you take an average of the variances? Do you standard deviation in control group? Do you standard deviation in experimental group? There is a thing called Glass's delta, which uses standard deviation in control group. Sometimes they'll use the standard deviation untainted by the experiment. So that's called delta for the univariate. Well, there is a multivariate extension of that. There's a multivariate extension that the book discusses briefly. But what we're going to do is show you how to use G-Power, which I have confirmed in one of my other softwares that I've paid for, gives me the same results. Say I have a standardized effect size of 1.0, which is pretty nice. That's one standard deviation difference as a multivariate effect size. Power of 0.8, 3 dVs. Do you see where it says response variables? I have 3 dVs. Add. I went ahead, add. Sample size, I decided to say, let's get 24 people in each group. So if you look on page 168, if I have a d squared of 1.0, if I go down, do you see where it says 1.0, everybody, for d squared? You'll see that in bold on across the side, d squared of 1.0. Number of variables go down to 3. You're going to go down to 3. And let's just go to the line that says n equals 25. N equals 25, and look, there's a power of 0.8 under 1. Does everybody see where I have, if you go to standardized effect size of 1, go down to where we have 3 response variables, n of 25, and then you see an 80 under the 1. Does everybody see the 80? That's your power, 0.8. 0.8, which means, you guys, I can get away with 24 people. 24 people per group. If I have.
Yeah, I was going to say,
That's
if
a
you have
nice, that's
one.
a big effect size. Johnson, I almost never do power analysis for large effect sizes. In fact, I just, this morning, someone from back east just sent me a protocol. I'm going to do a power analysis. And they give me an idea of effect sizes. I always assume they're from small to medium guys. I'm very conservative in power sample size estimation. I've only had one study. I've probably done well over 100 power analyses. I've maybe had 1 or 2 studies I've ever done for a large effect. And then some people say, if you have a large effect, what's the worth of doing the study in the first place? I mean, I've had some people say, use that logic. But again, I just want to show you can get away with a small sample size, but that means you have a large effect, which means that person who had to be doing that with 13 people, we weren't even close. We weren't even close.
What does it mean in the ones that have the parentheses, the number of parentheses in the table?
Oh, on the table? Okay, let's see. Let's see where. Oh, that's power for alpha 0.10.
What's that?
It's if your alpha is 0.10.
Okay.
All right. So you see 0.10, you don't need as many people, right?
But good luck if
You won't get published at 0.10. Now, would your boss know the difference? Would your boss at work really know the difference in 0.05 and 0.10?
No.
yeah, but that's unethical.
I don't know if your boss doesn't know. If you're not going to publish, you tell your boss I'm going to use an alpha of 0.10, and instead of 44 people, instead of 60, 60, I can get away with, 44.
So that's what you tell them that you're doing.
You're right. Yeah, exactly. It's not. That's what we tell them.
But you know they don't know.
Yeah, right.
So you can
So you'd have to
inform
tell
them.
them, you would have to tell them that you're being very
in the interest
conservative
of
or
full-
very
Right,
liberal.
full disclosure.
Would you be telling them you're being conservative or liberal?
Liberal.
Very liberal. You got it. You got it. So, here's, again, G-power to use the interface, everybody. You got the MANOVA, and you see hotel into t squared, two group mean vectors. This is what we did by hand. Hotel into t squared. And you put in the effect size, your power, and it returns to me. Now we can get away with 24 people per group, assuming equal sample size. Assuming equal sample size. And look, you can even, if you want to, you see there's number of response variables. You can put in a standard deviation correlation matrix. In other words, guess what? You've got to have an idea what the correlations are, the DVs. So I put in a 0.6. So you do have to put in a bit of information when you do a power analysis for a MANOVA. Now, what I want to show you is using D'Amaco's article, 2001, of Behavioral Research Methods, a correction article, and also a book that came out that I did part of my power analysis project that's got all the SPSS syntax. And you can do this in SPSS. And it's pretty cool, everybody. Let's say I have 3 DVs. 3 DVs, and I have a group. But look at the information you have to put in. Let's say I'm going to have 40 people per group, which means total sample size of what? For 2 groups. 80. But you have to put in what you think the means will be for 2 groups. You have to have an idea, you guys. You have to have an idea to do this in SPSS or SAS, these programs. I know the other programs I use, you have to have an idea of their means. So I think the mean for group 1 will be 25, 28, 29 on the 3 outcomes. You know, let's say job satisfaction, job involvement, and job stress. And the other is 21, 25, 23. Look what else I have to put in, everybody. Standard deviations and correlations. Lot of information you got to put in for power in a MANOVA. Now what if you say, Dale, I have 0 idea what it's going to be. Then you, in G-power, it does look like you can kind of put in maybe kind of an idea of an effect size. But here, you're really putting in a lot of information. You're really putting in a lot of information. And once you put that in, everybody, you run the MANOVA. And there it is. Look what it gives me, the power. Power 0.99. Pretty darn good, huh? So it's pretty cool, everybody. You can do a lot of power analysis with MANOVA and G-power, or you can even use the syntax in SPSS based on that article. And so this is something really should be done whenever you do a MANOVA. Again, you can either do this in SPSS, and here's some examples of syntax that you can use, or try using the G-power. Now what if I did 20 per group, everybody? Here I wanted to show you, in G-power, I put in what's called Glaser V. 2 groups, and it's the type of effect size, basically. I was able to say an effect size of 0.33, and this one uses Glaser V, which is one of the tested significance, 0.05, total sample size of 80, and look what it gives me, everybody. Same as SPSS, 0.99. Oh, I'm sorry, this was 40 per grade. This gives me the same. Same exact as the MANOVA, using the Pillay V, which is right here. The Pillay, O'Brien, Shea algorithm. I do want to show you, I redid this with 20 per group, 0.81. Which means, instead of 40 per group, you might as well get what? 20 per group. Save time and money and resources. But again, that means you have a pretty nice effect size. A pretty nice effect size. So everybody, that's kind of a more in-depth thing than you probably want on power, but you've got to be able to put in quite a bit of information when you're doing power analysis for MANOVA. You've got to have an idea of the means. You've got to have an idea of the correlations of job set and job involvement. So one way of getting at kind of an idea, if you have no idea, is your actual data, you can always do a correlation, right? Job sat, job involvement, and we see the correlation is 0.185. right? So sometimes you may have pilot data, you may have information out there. If you have no idea, everybody, if you literally have no idea, then what I do with my clients, I'll do something like this. Go to Excel. I'll do something. Let's assume 2 groups, 3 DVs. Let's just assume 2 groups, 3 DVs. I may have something like average. I may have effect size equals 0.2. Maybe something kind of small. Effect size equals 0.2. Effect size. And then I might have effect size equals 0.4, effect size equals 0.4. I'm just giving you effect size equals 0.4. I might vary there. And then I might have average R equals 0.2, average R equals 0.2, average. And I might vary at 0.4, 0.6. I may give, it's like almost like doing, I don't do simulations, I've done a little, but I'm not a computer, I'm not a programmer. I know somebody's in biotech, they'll do pretty fancy simulations for power, but I will give them a wide variety of small to medium. Then I'll vary the average correlations, and then I'll have the n per group, n equals 20, n equals 30, equals 40, etc. Per group, I'll give them different sample sizes, and then I'll give them that table. Then they'll either decide what their budget will allow, realistically, or if their budget is okay, they may go for the most conservative and get the larger sample size. So I at least give them an idea. I give them an idea of the range of estimated sample sizes given the varying parameters, small and medium effect sizes. Vary the average correlations of the TVs. And I do that for almost all my power analysis. I do that. And that's if they have zero idea. They say, well, and then I'll do it for small and medium. So that's power analysis. So let's go ahead, everybody. Any questions on this chapter? Let's go ahead and take 15, and then we will come back and start on chapter 5.